Hello, this is Philip Myers of PEMY Consulting. Welcome to Engineering Units for the Plant or Tank Engineer. This is part 7 on viscosity. Consider some different liquids. Ethanol, which is shown here, water, and honey. You know from experience that ethanol and water are very mobile liquids. They flow easily. Honey is less so. And of course, sludges and slurries and pastes are even less so. Viscosity is the property that governs the ability of the liquid to flow. So it's like this deck of cards. If you had a brand new deck of cards, you could easily push them and spread them out like that. If they were dirty and sticky, you'd probably only get that far. So viscosity is used in fluid flow problems all the time. It should be thought of as resistance to flow, and there are two types. The first is dynamic viscosity. This is typically measured in centipoise. We'll talk about those units later. You have to be careful that when you hear the word absolute, that's the same as dynamic. And then there is kinematic viscosity. That's very common also, and it is represented by Navier-Stokes. There are many other kinds of viscosity units such as SSU and many I'm not familiar with, but these are the two main groups of units. So you already know from experience that viscosity decreases with increasing temperature for liquids. Take the honey, for example. If you heat it up, it will flow faster. On the other hand, you may not be familiar with gas viscosity. It's of course a lot lower than liquid viscosity, but it also increases with temperature. A good example of where viscosity is used is in Reynolds number. This equation is a metric that determines the point where fluid flow goes from laminar, which means flowing like layers, like the cards, to turbulent, where a different mechanism of transport is occurring. Let's consider this setup that illustrates how viscosity works. We have a stationary plate down here with fluid in between it and a moving plate here. This plate is being pressed by a force and moves in this direction at a constant velocity u. Think of the layers as lamina. In fact, we're talking about laminar flow. As this plate moves, it causes these layers to slip past one another. The amount of drag between layers is, of course, related to the viscosity. There's another point that's important to understand, is that this layer, which is closest to the stationary plate, it is stuck to that plate. It doesn't move. I call it the sticky principle. It's also called the no-slip principle. The same is true with this layer. So this is stuck and moving with velocity u. So let's look at the animation and see what happens. So we see that with a little bit of time, what happens is, in this case, we're getting a linear velocity gradient. That isn't always true, and we'll talk about that later. But for this case, each layer is dragging the one below it at a constant amount. Now here's a typical chart you might find in a textbook. I want to point out a few things. The chart can be a little bit confusing. On this chart, you read the viscosity of water on the left-hand side, and on the right hand you read it for air. Suppose I wanted the viscosity at 20 degrees C. I would move up this 20 degree C line until I hit this point here for water. I would then move over this way and find 100. Well, what does the 100 mean? It says here mu PAS, so that can be confusing because mu, this could mean micro or it could mean viscosity. So one way to do the check is to do what I'm doing now. Make sure that it makes sense. So in this case, this is viscosity and it's dynamic viscosity. But it says I have to multiply by 10 to the minus 5. And so the unit would be 100 times 10 to the minus 5 Pascal seconds. That's how you would read that chart. Now here's suppose you wanted to know the viscosity of air. We would move up this line up to this point and read off here. So it's about 1.82. And by the same reasoning, we have to multiply by 10 to the minus 5. And this is Pascal seconds. Now here are some different ways of making a viscosity measurement. In this case, there's a little bulb that has a known volume in it. And what it does is it drains down and ends up in this tube, and there's a little orifice. You basically measure the time of drainage, and that is being done here. This device, of course, is much more sophisticated because it's maintaining a constant temperature. Other ways to do it are to put these propellers and rods or discs into a vat. These are small, and put them into a vat with a motor and measure how much force it requires to spin it at different velocities. And here is an example of a calibrated tube. You can see the graduations here, and they measure the drain down time of the liquid coming out of this device. So viscosity measurement in and of itself is a whole specialized topic. Now here we're going to talk about the physics of viscosity, and we're talking about absolute or dynamic viscosity. We have the moving plate, as we discussed earlier, with a constant force here on a plate of area A with a velocity u. This is the stationary plate, so it's fixed. And we have a distance here of liquid between the two plates, h. Here's the coordinate system. X is in the direction of the moving plate, and y is the measurement from the stationary plate upwards. Now we have assumed a linear velocity gradient, and that's shown over here. When it is linear, and fortunately it is the case with most liquids we typically work with, it is called a Newtonian fluid. Next we'll see examples that are not, but for the most part in typical tank engineering work we're dealing with Newtonian fluids. So stress, as you know, is the force per unit area. So stress on this plate, the shearing stress, which would be the resistance to this plate moving forward caused by the liquid, that is force per unit area. In the case of the moving plate, we have the shearing stress as tau, and that's supposed to be a constant times the velocity gradient. In other words, how steep this line is. So this is the velocity gradient. If we rearrange this for mu, and this is in fact the dynamic viscosity, well, let's just say it's Cp for centipoise, we can rearrange for tau divided by the velocity gradient. Well, this is pascals, so shear stress will be in pascals. du is the velocity rate of change, that's meters per second, and then dy is meters. After unit cancellations, we end up with Pascal seconds. That's the fundamental SI unit for dynamic viscosity in the SI system. If we rewrite that further to break it down into basic units, we can say that a Pascal is a Newton per square meter. The seconds stays as it is. If we write out the Newton and do some unit cancellation, so the meter here cancels with the meter here in the numerator, and the second here cancels with the second here, we end up with kilogram per meter second. Mass per length time is the fundamental units of dynamic viscosity. Now, as I mentioned earlier, not all liquids are Newtonian fluids. The whole topic of the linearity of viscosity is called rheology. So here is the Newtonian fluid, just a straight line on this plot of velocity gradient du dy versus a shear stress tau. Some liquids I call pseudoplastic fluids. They do that, and that means that they are thinning as a velocity gradient increases. They're shear thinning liquids. So an example of this would be paint, latex paint. It doesn't flow very well on the paintbrush, but when you hit the wall with it and start moving, it flows out much more readily. There are other fluids that can do the opposite. So cornstarch in water is an example of a dilatant fluid or shear thickening fluid. And yet there are other examples of fluids that require a minimum amount of stress, a yield stress, for the fluid to even begin to move. So toothpaste is an example. It'll just sit there in a pile, but when you apply enough pressure it will start to flow. So it has a point here that's above zero that's required to get it moving, but once you get it moving it has a linear flow pattern. Those are called Bingham plastics, and of course there are non-Bingham type nonlinear fluids. They're all much more complex to work with the linear Newtonian fluid properties. Here we'll talk about the basic units of viscosity. There is dynamic viscosity, and the unit for that is the poise, and there is kinematic viscosity, and there is the unit of Stokes for that. These units can be a little confusing and hard to understand, and one of the reasons is that they were developed in the CGS system. C is for centimeters, grams, second system. The system is now obsolete according to the SI system protocol, but it is still sometimes used. Force in the CGS system is defined as a dyne, and that is a gram centimeter per second squared. You'll see the analogy to the SI unit of force, the Newton. There are 1,000 grams in a kilogram and 100 centimeters in a meter. Therefore, this unit, the dyne, is 100,000 times smaller than the Newton. Pressure is dynes per square centimeter or grams per centimeter per second squared. So let's convert the poise to SI units. It is defined as 1 dyne second per centimeter squared. This is a force or a pressure time unit, just as the Pascal second is, so it is a viscosity. If we break that down into its fundamental units, we see that the centimeters cancels, the seconds cancel, and we end up with a gram per centimeter per second. That has dimensions of mass per length time. Now that is not an intuitive unit, but this is the dimensional grouping for a dynamic viscosity. It's useful to know because you can check your work for mistakes by checking this. The poise then is a gram centimeter per second, and we convert to kilograms by getting rid of the grams, and also to meters by getting rid of the centimeters, and we're left with 0.1 kilogram per meter per second. So a poise is 0.1 Pascal seconds, and 1 Pascal second is 10 poise. So this is the conversion you need to be aware of to get back to your basic group of SI units. 1 centipause, of course, is 1/100th of a poise. The poise is too big to work with in general, so it's typically the centipause that we work with. 1 Pascal second is therefore 1,000 CP. You'll sometimes hear or see the term millipascal, and it's just what you would think. It's 1/1000th of a Pascal second. So therefore 1,000 millipascal seconds is the same as 1,000 CP. And this is another useful relationship to remember. Now for kinematic viscosity, it's a different unit altogether. It is the grouping of dynamic viscosity divided by density. Why do we have this unit? It turns out that mu over rho occurs so frequently that it's worth having its own symbol, which is nu, and its own nickname, kinematic viscosity. If we break down the units, we can do like we did before and take a Pascal second divided by density units. We then end up with newtons per square meter seconds divided by the density units. I'll let you, as an exercise, cancel these units, but you ultimately end up with meters squared per second. So the dimensions of kinematic viscosity are length squared per time. Here again, it's not intuitive, but those are the fundamental dimensions of kinematic viscosity. Now, Stokes again was defined in the CGS when Stokes is defined as 1 centimeter squared per second. Since there's 100,000 centimeters in a square meter, in SI units there's 10 to the 4th Stokes per meter squared per second. So 1 centistoke is a more reasonably small unit. That's 0.01 stoke. If we convert that to millimeters, we'll end up with 1 millimeter squared per second. So 1 centistoke is 1 millimeter squared per second. This is also useful to use when you're working with viscosity so that you can quickly convert between dynamic and kinematic viscosity. So we saw that 1 centistoke is the same as 1 millimeter square per second. Another useful thing to know is that there are 1,000,000 square millimeters per second. That's because there are 1,000,000 square millimeters in a square meter. That means that there are 1,000,000 centistokes, 10 to the 6 centistoke, in 1 meter squared per second. So this is sometimes a useful relationship as well. When you're working with viscosity, you'll be using tables like this. The most reliable source is textbooks, but the internet has good information too. You have to be careful with these tables, and let me illustrate that. Here is a viscosity for water and air. Now at room temperature, let's say we're close to room temperature, that's 20 degrees C. This says that the viscosity of water is 100.2. So that's 100.2 times, now we have to put 10 to the minus 5 here because this says this unit is in 100,000 times bigger than what the number is here. So this is equal to 0.001002 Pascal seconds from these units stated here. Now recall that a Pascal is 1/1000th, a CP, a centipause, is 1/1000th of a Pascal second. So we can say that this is equal to 1.002 centipoise. Now let's take a look at kinematic viscosity for air. We see this is 1.004 times 10 to the 6. So we have to divide this by 1,000,000. So this would be 1.004 times 10 to the minus 6 meter squared per second. But we recall that there are 1,000,000 millimeters squared in 1 meter square. So this is 1.004 millimeter squared per second. But we also know that that is 1 centistoke from our previous slides. This slide goes over what we went over in the previous slide, but formalizes a little bit so you can see the details of the calculation. We have water in Pascal seconds, a viscosity of 100 times 10 to the minus 5. We want to know what the kinematic viscosity is in centistokes. So we take the 100 times 10 to the minus 5 Pascal seconds. There are 1,000 CP per Pascal second, so we know that that's 1 centipoise. But we were asked for kinematic viscosity, nu, and that is mu, the dynamic viscosity, divided by rho. Here again we use the SI unit of Pascal seconds to keep things straight. this number is the same. The 100 times 10 to the minus 5 is the same as 1 times 10 to the minus 3, and we divide it by kilograms per cubic meter. I'll leave it as an exercise for you to go through these cancellations, but we end up with 1 millimeter squared per second. Now in a previous slide we learned that 1 millimeter squared per second is the same as 1 centistoke, so that is the answer. It's useful to know that 1 CP is the same as 1 centistoke, and this is only true when the water density is 1,000 kilograms per cubic meter, so you have to watch out when you're working with other temperatures or pressures and so forth. Sometimes you'll see plots like this where the viscosity is given in kinematic viscosity. So in this example we want to convert the viscosity of air at 20 degrees C using the chart. We want to convert it to centipoise. So we'll assume that air has a density of 1.2 kilogram per cubic meter. So the first thing we do is look at the temperature, 20 degrees C. We read up the vertical axis until we hit this number, and then read over here. So you can see the accuracy can't be that great, but this is 10. This is a log scale. This would be 20. So we'll call that 15. So we have 15 times 10 to the minus 6. Now in this scale they actually give the units as directly as 10 to the minus 6. So we have 15 times 10 to the minus 6 meters squared per second, but we have to multiply now because mu is equal to nu times the density. So multiplying that out, we get meter squared kilogram per second per cubic meter. The meter square here cancels. This cancels, so we have kilogram per second meter. Now you know that that is a Pascal second. So this works out to 18 times 10 to the minus 6 Pascal seconds. And that can be rewritten as 1.8 times 10 to the minus Pascal seconds, or because there are 1000 CP in a Pascal second, we have 0.018 centipoise. So I hope that this unit on viscosity units helps you work with viscosity more effectively. It's a little bit tricky to work with viscosity, and there are very many other unit systems for viscosity. One of the common ones used in the oil industry is Sabelt seconds universal, or SSU. In those cases you have to research the conversion factors carefully and do the same kinds of checks that we did here to make sure that you're not orders of magnitude off on your projected answer. Thank you.